The greatest theorem in history, Bayes' theorem. Throughout our history, numerous significant figures and concepts have emerged, but if we were to highlight one particularly shining theorem in the fields of statistics and probability, it would be the famous Bayes' theorem. First introduced by the 18th century British mathematician Thomas Bayes, this theorem has long inspired many with its unique characteristics and innovative approach. Recently, it has gained explosive attention, especially in new fields like machine learning, where its application has become increasingly essential. Bayesian machine learning, which utilizes Bayes' theorem, deals with uncertainty and probabilistic inference from data. The application of Bayes' theorem in machine learning improves predictions based on observed data and manages uncertainties, allowing for more robust forecasting. It is now an indispensable tool in almost all AI fields, from general machine learning to the latest popular artificial intelligence like ChatGPT. Core principles of Bayes' theorem. Bayes' theorem plays a vital role in many situations surrounding us. In fact, our unconscious thought and reasoning processes in daily life align with Bayes' theorem. Essentially, this theorem calculates probabilities based on observed data. For instance, it's used to infer whether a cold medicine was effective after consumption. Let's say the probability of having a certain disease is denoted as A, and the probability of a positive test result for the disease as B. We want to know about A, whether we have the disease, while our available information is B, a positive diagnostic test. This is called the conditional probability of event A, denoted as probability of A given B. Event A, being in a state of a specific disease. Event B, testing positive for the disease. Probability of A represents the probability of event A occurring, and probability of B is the probability of event B occurring. Here, probability of A given B denotes the conditional probability of A occurring, given that B has occurred. Bayes' theorem calculates probability of A given B, using probability of B given A. This approach is chosen because it's often much easier to determine the latter condition. Probability of B given A is usually known or easier to calculate. For example, we often want to estimate probability of A given B, the probability of having a disease given a positive test result. However, in most cases, we can't directly know this probability without previous repetitive tests. On the other hand, probability of B given A, the probability of a positive test result if one has the disease, is more commonly known. This data is typically obtained through clinical trials and distributed with test kits. Other information, such as the overall prevalence of the disease probability of A, and the general probability of a positive test result probability of B, can also be estimated or is somewhat known. Combining this information allows us to estimate the probability of having the disease given a positive test result. This way, Bayes' theorem aids in making more accurate decisions in inference processes across various fields. The Monty Hall problem. Let's understand the concept of Bayes' theorem by solving the Monty Hall problem, a classic example of how intuitive probability can lead to incorrect conclusions. The Monty Hall problem is a famous probability theory puzzle, popularized by the American TV game show Let's Make a Deal, and named after its host, Monty Hall. It's a well-known example of the gap between probability theory and human intuition. In this example, we'll see how the combination of new information with Bayes' theorem leads to a conclusion different from our intuition. Problem description. The Monty Hall problem is set up as follows. A contestant can choose one of three doors 1, 2, 3, behind which prizes are hidden. Only one door has a valuable car prize while the others have goats, intended for humorous effect. Suppose the contestant chooses door 1, then host Monty Hall opens one of the other doors, say door 3, revealing a goat. The contestant is then given a chance to change their choice. Should they switch their choice or stick with the original? Intuitive thought. Many people initially believe that even after the host reveals a goat behind one of the unchosen doors, the car remains equally likely to be behind any of the doors. They intuitively think that it doesn't matter whether the contestant changes their choice or not. However, changing the choice actually doubles the probability of winning the car. To understand why, we need to apply Bayes' theorem. Proof. Let's use Bayes' theorem to prove this. Suppose the probability of the contestant choosing the car door is H, and the probability of host Monty revealing a goat is E, where H and E stand for hypothesis and evidence respectively. Many people get confused in this problem because they don't properly understand how the new information affects their choice. We need to calculate and prove what changes occur after updating the information that there is a goat behind door 3. Initially, the probability of choosing the car door, probability of hypothesis, is of course 1/3. What we need to calculate is how this probability changes after observing the evidence of the goat, that is, probability of hypothesis given evidence. In this application of Bayes' theorem, we simply replace A and B with H and E. Firstly, probability of hypothesis represents the car is behind the door I chose, which is 1/3 given 3 doors. Probability of evidence given hypothesis is always 1, because Monty, who knows where the car is, will always open a door with a goat to avoid a show mishap. Now we just need to calculate the probability of event E. If the contestant had chosen the car door, Monty could have opened any door to show a goat. If the contestant had chosen a goat door, Monty would have opened the other goat door. There are 2 cases in which E occurs. The contestant chooses the car, and Monty opens any door to show a goat. The contestant chooses a goat, and Monty opens the other goat door. In both cases, Monty opens a door with a goat, making the probability of E1. Now we can calculate the posterior probability, that is, the probability that the car is behind the door I chose, after observing Monty showing a goat. C. The probability remains the same at 1/3, even after Monty Hall provides additional information. This means that the probability of winning the car by initially choosing door 1 was 33.3%, and even after Monty shows a goat behind door 3, the probability remains 33.3%. Importantly, the probability of the car not being behind door 1 is 66.7%. Originally this 66.7% chance was split between doors 2 and 3, but now with door 3 opened, door 2 holds the entire 66.7% probability, therefore the conclusion is clear: the contestant should switch to door 2 to double the chances of winning the car. In conclusion, in the Monty Hall problem, always changing the initial choice increases the probability of winning the car. While the initial probability of the chosen door having the car is 1/3, changing the choice after Monty Hall reveals a goat door increases the probability to 2/3, doubling the chances. We have mathematically proven this using Bayes' theorem. Applications of Bayes' theorem. Bayes' theorem is broadly used across various domains and technologies regardless of specific fields. For instance, in medical diagnostics, Bayes' theorem calculates the likelihood of disease based on patient symptoms and test results. In finance, it's applied in stock market predictions and insurance rate calculations. In artificial intelligence, especially in causal modeling, Bayesian networks and other modeling techniques utilize Bayes' theorem, playing a vital role in most machine learning algorithms. Bayes' theorem is innovative, even from the time of its introduction, particularly in its ability to update posterior probabilities based on prior information and new data. It suggests the possibility of improving predictions as new data or evidence emerges. This approach remains a fundamental and crucial principle in modern statistics and artificial intelligence. Conclusion. Bayes' theorem is a powerful tool in dealing with uncertainties we face in the real world. It allows us to estimate and predict the probabilities of events from limited information and incomplete data. By incorporating new information and updating prior probabilities, we can calculate more accurate posterior probabilities. Recognized as one of the greatest theorems in history, Bayes' theorem is extensively and indispensably used. Its innovative nature and applicability are increasingly recognized across various fields, including modern statistics, artificial intelligence, and medicine. Bayes' theorem provides a strong basis for our decision-making and problem-solving in exploring and judging uncertainties. Therefore, understanding and applying the principles of Bayes' theorem can enhance our ability to solve complex problems.